Welcome back. So what we're going to do now is we're going to start digging into this idea of defiance. And we're going to consider a number of different case studies, each of which will be interesting in its own right. The first one we're going to tackle has to do with defying the laws of diffusion. The fact that if I have concentration gradients, that those concentration gradients will dissipate over time unless there's some active mechanism keeping them in place. So that'll be case number one. We'll also look at fidelity, and that'll be our second kind of defiance. And what I mean by that is most easily illustrated by considering an enzyme. Let's say if there's an enzyme that has some substrate, which is the right substrate, and then there's some competitor substrate, which is the wrong one. And the equilibrium fidelity for that process would be the ratio of the KDs, basically. And I'll explain that later. But it turns out that there are biological examples where the fidelity is way higher than what you get out of the ratio of the KDs. And so that's a certain kind of defiance. We'll also talk about adaptation, and what that will be a kind of defiance of is the conventional Langmuir binding curve. What I mean by that is you'll recall that the Langmuir binding curve, it has a particular dose response, and it may turn out that the concentration, the midpoint concentration, the system may want to change that. An example of this would be in chemotaxis. If I change the overall background ambient concentration, the chemotaxis receptors should still be able to detect gradients. And they have a clever way of shifting the middle point of their dose response curves that we'll also talk about. So the first case study is this one, which is defiance in the diffusive sense. So I just want to point out that cells have concentration gradients of ions, for example, as you see here. You can see that the concentration of sodium within the cell is lower than it is on the outside. Similarly, the concentration of potassium inside of the cell is higher than on the outside, and those two are coupled by a transporter that moves both of them against their gradients at the same time, but through the consumption of energy. So this particular vignette is concerned with only one question. And that is, and it's a part of the total calculation that we're going to need to do. In other words, it's going to take us several vignettes to work our way through this general question of the free energy cost to maintain a gradient and why this is a kind of defiance. And what I'm going to do here is simply the following question. I'm going to ask if there are L1 ligands on the left-hand side of this partition, if there are L2 ligands on the right-hand side of this partition, and the daemon allows one molecule to pass from right to left such that now there's L1 plus 1 on the left and L2 minus 1 on the right. My goal is to compute the free energy change when the daemon does this, okay? So the way that we're going to do this is we're going to calculate the change in free energy, and I want to point out right here at the outset that I'm going to be casual about the difference between the Gibbs and the Helmholtz free energy. I know the difference between them, and I like the difference between them. But we're not going to worry about that. So I'm simply going to say that U captures either energy or enthalpy, and I'm going to be indifferent to that. I'm also going to claim here that the delta U is equal to 0, and the reason for that, let me just quickly show you. U initial is equal to L1 times epsilon solution plus L2 times epsilon solution. And U final is equal to L1 plus 1 times epsilon solution, and plus L2 minus 1 times epsilon solution. What I've done is I've just looked at the left and the right-hand sides, but this is equal to L tot, or L1 plus L2 times epsilon solution, and this is also equal to L1 plus L2 times epsilon solution. So all the particles are embedded in solution, and when I move them between the different sides, it doesn't change anything with respect to the energy, the internal energy. So effectively, everything comes down to reckoning the change in the entropy. The change in the entropy is going to be equal to KB, and then times log of W left final, where there's L1 plus 1 particles on the left side, and W right final, where there's L2 minus 1 particles on the right side. And then I subtract from that KB log of W left initial, for which there were L1 particles, and WR initial, when there were L2 particles. All right, so just to make sure that everyone's on board with what I'm doing here, what I've said is that the way I compute the entropy is I take the logarithm of the total number of states. The total number of states is the product of the number of states of the left times the number of states of the right. They're independent. In other words, the rearrangements that I do over here on the left-hand side are not coupled to the rearrangements I do on the right-hand side. And so just like I said in a previous vignette, if I'm flipping a coin and rolling a die, then I have 2 choices for the coin, and I have 6 choices for the die, and I have 6 times 12 choices for the total number of ways of realizing a particular experiment. The same thing is going on here. So I can rewrite this as being equal to KB. So let's now write delta G is equal to minus KBT, and then I have logarithm, and I'm just going to grab these pieces here. So this is my numerator right here, and I divide by the denominator, which is the second piece here. So that's the entropy change. It's just given basically by the ratio of the number of states that are available to the system. And now it comes time to actually write what we have in mind. So what is W left initial? Yikes, I'm sorry, I brought too much junk downstairs when I did my little copy. I thought I was being clever, but I ended up being sloppy, so I'm sorry. W left initial, L1 and omega, is equal to omega to the L1 power over L1 factorial. This is my stadium seating analogy, where we have very few attendees at the stadium. So I have 60,000 seats, I have 30 people attending, and I offer my hat that has the numbers for all the seats. There's 60,000 numbers. Person 1 picks a number, they look at it and they put it back, and I shake it up. And the thought is that the approximation I'm making, or I should say the caution that I'm making, or that I'm assuming, is that I'm never going to have 2 people grabbing the same number, because there's just too many seats available for those 30 people to be drawing from. The probability of 2 people drawing the same one is very small, and so that inclines me to this idea that every person has omega choices. I remind you again, the denominator has to do with the fact that who's sitting in the seats, everybody's wearing gray. So if I switch gray shirts, there's L factorial ways of switching them around. So given this, I think I'm straight away ready to write down the total delta G. So delta G is equal to minus KBT, and then log, and then I have omega to the L1 plus 1 over L1 plus 1 factorial over omega to the L1 over L1 factorial, and then times omega to the L2 minus 1 over L2 minus 1 factorial, and that's all over omega to the L2 over L2 factorial. So that's the total. That's each one of those is a piece of the total number of states. So this is the number of states. This piece is the number of states available to the left-hand side when I have taken an extra ligand on board. This is the number of states on the left-hand side initially. This is the number of states on the right-hand side after I've removed one of the particles, and so on. And now I can simplify. This ends up being equal to omega over L1 plus 1. This one ends up being L2 over omega. And so this guy is approximately equal to 1 over the concentration of L1, and this one is the concentration of L2, and so what we're left with is that delta G is equal to minus KBT, and then log of L1, log of L2 over L1. Yeah. So that's our result. I mean, I'm done. What I've figured out is the free energy difference when we take a molecule from over here and move it over to the other side. Given that there were L2 on the right and L1 on the left initially, now what we've done is we've moved one of them, and we've seen that the free energy associated with that is of the form KBT log ratio of the concentrations. Note, so this is our final point, note, if, let's first of all rewrite, I'm going to rewrite this as delta G is equal to KBT, and then log of no, I'll leave it alone. Sorry, I'm sorry. I'm kind of anticipating something that's going to happen later. So let's say that this is equal to minus KBT, and then log of 10 to the n L1 over L1. What am I doing here? I'm assuming that L2 is 10 to the n-fold bigger than L1. I'm not making any scientific statement about what I actually think is happening in the world of concentrations. I'm trying to make a point, which is I'm trying to show you that for every 10-fold increment in concentration change, it's worth roughly 2.3 kBTs of energy. So, I can cancel these L1s. Basically, I'm just writing L2 is proportional to L1. I'm just giving you some proportionality constant. And so I plug that in, and this leaves me with minus KBT, and then log of 10 to the n, which is equal to minus n KBT log 10, which this log 10, I hope you remember, is roughly 2.3. So this whole thing is minus 2.3 n KBT, and so we see that a 10-fold excess on one side relative to the other is worth 2.3 kTs. If I have a 100-fold, it's worth 4.6 kTs, and so on. So this is just trying to give you a sense of how much energy, free energy, can be harvested from a given gradient. How much weightlifting can we do on the basis of such a gradient? And I'll come to that in a future vignette. For now, just again, the reminder, we computed one piece of what we're going to need. We've computed the free energy change of bringing one particle, and the next thing we're going to do in the forthcoming vignette is we will work out the total change because of the presence of diffusion. And so there'll be a flux, and every molecule will carry this particular delta G, and so we'll have to put all those together to get a total.